So, hi everyone, my name is Mahrukh and I'm assistant professor in electrical and computer engineering department at the College of New Jersey. The topic of my talk is analysis of modal excitation of slot-loaded microstrip antennas using degree of characteristic modes. Before starting, I just want to introduce myself. So I recently joined the College of New Jersey as an assistant professor. Previously, I was working in MIDE, affiliated with University of Missouri, Kansas City as an assistant research professor. I did my PhD in 2017 with UMKC. I've been working, it's been, I think, for more than 4 years, I've been working on characteristic modes. I started working on them during my PhD. Today, in my talk, I will be talking about my recent paper that has been published in IEEE Transactions that is related to the modal excitation of wideband slot-loaded antennas. So before, when I was starting work on this problem, I had two questions in my mind. The first question was, can feed change the modal behavior of antenna structure? If yes, then can natural modes of antenna predict modal behavior after feed excitations? So I tried to address these two questions in my paper, and I will talk about them today as well, briefly. So when I was started my work, I found very interesting paper by Dr. Haas regarding antenna modes and the scattering modes. As we all know that modal excitation coefficient can be given by this expression where Jn are the modal currents and the EI is the impressed electric field. So in this paper, they talk about that impressed electric field can be represented as E incident and E feed, where E incident is the field incident on the antenna, and E feed is the field induced at the antenna feed point. So, and then your modal excitation coefficient can become this. So when they talk about, they said that if your field induced at the antenna feed point is not equal to 0, then you are saying that you're working with antenna modes. And when they are equal to 0, you're working with the scattering modes. So that's very interesting, I think, if we talk about excitation at the feed point. So thinking about this, I actually divided my research in 3 parts. I was working on U-slot antenna. So I said that one part is antenna structure. The second part is antenna with feed before excitation, when we introduce feed in the antenna, so the feed structure in the antenna. So the second part is the antenna with feed before excitation. So I actually explored 2 types of feed. One was the straight probe feed and then L-probe feed in this research. And then I said that the third part is that if I excite the feed, what will be the behavior? So I will try to address all 3 scenarios in this talk. So first, if I talk about just the structure, I said that, okay, as we all know that total current distribution on the surface of the antenna is actually this expression, and we know that total current can be represented as the summation of modal weighted coefficients and then modal currents due to the patch. One more thing, I said that if I'm just talking about the structure, these are natural modes, because these are the modes that will be created by the structure, or they're just the antenna. And we say that these modal currents will be the modal current due to the patch. So I looked at the modal significance of the just the structure, and found that there are I am looking into the 10 modes, and you can see that the J1 here, like some modes are narrowband modes and some modes are wideband modes. Like if you see here J1 is showing you modal significance as 1, but it's a narrowband mode. So when we talk about the bandwidths of the modes, because we are talking about ultra wideband antenna, So bandwidths of the modes are also very important. So we say that bandwidths of the modes are when they are range of frequency we define between upper frequency and lower frequency, thinking about modal significance is 0.707. So we can see that some of the modes are really, really wideband, like here in the J5, it's a really wideband mode. And there are also higher order modes in this structure. So thinking about this, these are just the natural modes, and these are the modes with just the structure. So I also looked into the surface currents of the modes, and these are all surface currents where I am getting the maximum modal significance. Like I can see that if you see that J1 and J2, they are purely horizontal current modes and the vertical current modes. But if you see J3, it is also showing you the diagonal currents around this U slot, but the vertical currents within the U slot. As you move towards the higher order modes, you can see that your current is concentrated within the U, and outside the U, it's either diagonal or they are canceling each other. Similarly, if you see J4 is showing you the modes that are canceling each other. So I think that this mode may not contribute into the total bandwidth, but we will see about this. So these are the modal surface current of just the structure. So this is just the natural modes of the structure. So if I am moving to the second part of my research, I'm saying that let's introduce a feed structure into the U slot and see what will happen. So when I introduce the feed structure, two types of feed I am addressing, the straight probe feed and L probe feed. So then I said, now this structure is modified because of the introduction of the feed. So now my modal current, which were JN before, after the feed inclusion, I can say that they are JNF because there is the feed in it. So then another paper I found very interesting is that they were talking about the currents in which they were saying that the currents are due to the patch. The total current is the summation of the currents due to the patch and then the feed. So if I think about that, like I am saying that modal current due to the patch, which I have defined before when I was talking about natural modes. And then I said that these are the modal current due to the patch and these are the modal current due to the feed. So my total JN is the combination of both the currents. So that's another interesting aspect of the feed structure. Then if we think about the paper that we were previously talking about, we are saying that modal excitation coefficient is the combination of the field due to the incident field and the field due to the feed. But here, right now, I'm not exciting my feed yet. So this is 0. And I said that my modal excitation coefficient before excitation is just due to the incident field, or it's just a scattering mode I am operating on. So now if I move and I think about just the feed, I said, let's compare the inactive feed. Inactive feed means that we have the fields, we have the feed in the structure, but we have not excited it. So now we have the field in the structure, feed in the structure, and we see that our natural modes, which are the A figure, our modal significance due to the feed structures are changed. So let's see if we see the straight probe feed, we can see that there are some higher order modes there. So, but also we can see that our J3 is a little bit changed. It becomes little bit narrow. Our J2 is very excited a little bit better than the natural modes. And similarly, we are seeing some introduction of new modes as well, which were G15, J16, and other modes as well. Similarly, if you see the L probe graph, like the plot, you can see that you are seeing some more higher order modes, some more very, very wide band modes. Like if I see J35, it's a band with 100% bandwidth because it's for the whole bandwidth is almost 1. So it's it's very interesting to see that because of the feed structure, we are seeing a different modal significance. So thinking about this, now I will move towards the third part of the thing. If I say that, okay, now if I excite my feed, what will happen? So we say after excitation, the effect of antenna feed point can be represented by its input impedance. And now, because our feed point electric field is not equals to 0, so after excitation, our modal excitation will be, vector will be this. So now I am talking about the feed with the excitation. So now if I move towards my analysis, I think that now if I just think about straight probe feed, I said that, okay, now after excitation, these are my modal significance plot of the straight probe fed U-slot antenna. I will compare it at the end to say that what was happening before excitation and with the natural modes. But here we are seeing that there are multiple modes that are excited, but within our bandwidth we were looking into, there were 3 modes that contributed, like J3, J14, and J6. There was one more mode, if you can see here, that is J9, but the mode is, as we talked about, that they were canceling each other, so it did not participate in the bandwidth. So thinking about this, we can see that J3, J14, and J6 participated in the bandwidth. If you remember the surface current that I have presented before, you did not see this presence of the feed here, if you remember. So this presence of the feed, if you see, are showing the localized, the presence of the feed due to which the currents are even emerging or going towards that. So this shows that the straight probe is excited and it's there in the U-slot antenna. So now we have 3 modes that participated in the bandwidth. Now, if I move towards the L probe, I say, okay, so there are, of course, higher number of modes that were there, and then higher number of modes because we were seeing very, very wide bandwidth with the L probe. So more number of modes that have been participated in the bandwidth. So we can see here that one of the mode was J7, which canceled each other, so it is not participating in the bandwidth, but all the other modes are participating in the bandwidth, like J3, J2, J35, and J70. And another interesting aspect, you can see that because this is electromagnetically coupled port, that's why you are not seeing any, contact here. You're not seeing any current that were emerging from there or going from there. So it's because of the L probe feed. So after doing the analysis of all three types of the feed, if I move forward and summarize this scenario, what I found is that due to the straight probe feed, these are the natural modes that were excited initially. They participated in the modal significance. They were there in the modal significance for the straight probe feed and for the L probe feed. They were excited, like J1, J3, and J6. Similarly, in L probe feed, 3 modes were excited, J1, J2, and J3. Sorry. 3 modes were excited, J1, J2, and J3. So, but if you see now the contributed modes that contribute in the bandwidth, they were even less. So J3 and J6 contributed in the total bandwidth, and J2 and J3 contributed in the total bandwidth. We were, of course, seeing a very, very large bandwidth with the L probe. So it means that the modes of the structure that we found using modal significance without the feed, some of the modes, initial modes were there, but there were some new modes that contributed in the bandwidth. So few natural modes participated, but there were some new modes. So it means that feed is playing a very, very important role in modal characterization of the antenna. So if we move forward, so this was my summary from the whole analysis. And if you see here, this was my natural modes without feed. Here, NB represents narrowband, BB represents broadband. So if you see here, some of my modes are showing modal significance as 1, means that they are well excited. Some of them are showing less modal significance. So it's not very well radiated or excited. So, radiated. So if you see here, these were my natural modes, but we can see that they're like after the feed induction that there were some different modes as well. So if you see here that in straight feed, when it was inactive and when it was active, means when it was excited, we can see that some of the modes that are not there and some of the modes were there. So what I found that the modal significance due to the straight P when it was inactive and modal significance or the modes that were radiated when it was active, they were not equal to each other. There were some new modes, then there were some modes that were absent. So what I is that the modal eigenvalue not equal. Now, if we L-probe feed when it was inactive, and I said that if you can see that the modes are almost similar to the L-probe mode when it was inactive and active. So they both were the same. So we can say that mode, like the modal eigenvalues for the L-probe feed after excitation is equal to the modal eigenvalue before excitation. So that's very interesting result. I think that the attachment mode due to the straight probe feed plays an important role in this case, because we can see that before excitation and after excitation, our modes have been changed. So that's I think very important result to know when we predict our modes by putting the feed in it, that if it is a feed that is touching the conducting patch, then your modes can be different that will participate in the bandwidth. So if I summarize this, I can say that the natural modes give us intuitive insight, but the feed excitation plays a very, very important role in the impedance bandwidth. And as well as we can also say that you can predict using inactive L-probe feed, the modal behavior of L-probe feed antenna, but you cannot predict with the straight probe feed excitation the antenna's modal behavior. So it's very important to see that as well. Another thing I think is that we said that we can see more of the diagonal currents in L-probe because, of course, because higher order modes were excited and it was large bandwidth, that's why. And another thing we are saying that the current modes which were canceling each other did not take part in the impedance bandwidth. That's about it. If you have any questions, I hope I was not too fast.
Thank you, Mahrukh, for your speech. Are there any questions?
I had a question.
Yes, please.
So thank you for your nice presentation. I had one question that you showed the eigenvalue of the straight probe in active and inactive scenarios are different. And I think this can be described by the impedance of the feeding, because when you're in active mode, your feeding is 50 ohm. And then when you're in inactive mode, you basically you have a short circuit or you're shorting the feed. So that's why the eigenvalue of these two structures are different. So do you think is this the reason of this different eigenvalues, or it has another reason?
I feel because the thing you're talking about, it is the same as L-probe, right?
for the L probe, we are not directly connecting this capacitive like feeding to the structure. So maybe we cannot see so much effect of this 50 ohm or short circuit. But in the case of a straight probe, maybe this effect is more severe.
I think that is related to, I feel that is related to attachment modes, because when you attach your structure to the, the conducting patch, it actually creates more currents than when you have the electromagnetically coupled mode like structure. But I feel that it's very important. We should do more research on it, that why this thing is happening. Yes.
Okay, thank you.
Okay. I also think that it's because of the shorting, because when you are not putting any source in the straight probe, you are connecting the structure to the ground plane. So you have a new condition, you have open, short, and this changes the resonances. It's a lambda over 4, probably resonator, or it has some impact on the, a well-known technique is connecting to the ground plane in order to reduce the size. So I think when you excite, there is no longer a shorting there. There is no, I don't know. I think it could be also a reason.
Yeah, I think we should include that in mathematically as well, in the modal current expressions, that what is happening when we have the attachment mode and what is happening when we have the electromagnetically coupled feed.
Anyway, I think it's a very interesting point, and it may be taken into account for future designs.
Yes, thank you. Yeah.
Okay, more questions?
May I ask regarding the same point, actually, and I don't know if you excite or not excite, if that changes anything in the impedance. This I'm not sure, but I think if you want to maybe make more deeper things into this, so it could be because of the fact that some modes will require you to have a connection, which means a current flow. And once you have this connection, those modes will be excited. But if you don't have that connection, you can't. It's something like, maybe you can look at it, these waveguides, which are excited at the short wall with a very short pin. Not like the normal pin, which is in the air, but rather from the other wall, when you have the pin, which is then shorting to your wall, because you cannot, some of the modes will require you to have this connection. So maybe you can look into that to know this difference.
Yeah, okay. But my question was that we have the excitation in both of them, right? We have the excitation in straight probe, and we have the excitation in electromagnetic coupled. So I think I found it interesting that why we are seeing the difference. Then I do a lot of research, and I found that there is something that is, I all the time going back, because I am also doing more research towards it, that why it's happening. But I think we should be doing more work on this to see what is happening.
Yes, sure. And your results for the simulations are impressive, because you have arrived to mode number 70. Wow. I mean, you have been computing a lot of modes. That's very difficult to identify. So, wow, I was impressed.
Yeah, thank you. I'm just more obsessed with the current modes. And I read your thesis a lot of times.
Okay.
Mahrukh, you have got a question in the chat, if I may.
Yes.
Give it to you directly. So it's from Imran, who says, how can we generate the modal significance plot versus frequency by using HFSS?
I think HFSS is not having the current, like the characteristic modes solver yet. CST has,
but I'm not an expert.
I don't use it actually. Yeah, okay. I use CST and FICO. In the previous version, they were not having. I don't know, did they have it now? Evita?
I think they have it, but I've not used it, so I'm not an expert.
Yeah,
in that. I
use CST and FICO.
Okay. So are there any more questions? You might you might want to speak before we switch to the next talk.
Vincent here. So yeah, I think I can confirm that ANSYS have this capability now. I don't think they have implemented the model weighting feature yet, but they have just to find the eigenvalues, they can do it on model significance. But I also have a question. I'm sorry, I can't raise my hand. I think it's because I'm a co-host.
Yeah, could be.
But I have a question. So the difference is, like for instance, on this slide, between the straight probe inactive and straight probe active. Hania just now mentioned this, right? When you do the active one, it is because I think inherently there is a 50 ohm. It's like having a 50 ohm resistor attached across the probe, right? And this is why you have the difference. So I just want to check with you that this is what you did, and which software did you use for this? Because in FICO,
I use 50 ohm, yes.
Okay,
the port impedance, yes, and I use FICO, yeah.
Right, because FICO, if you just excite it, normally it is assuming, I think it is assuming just a short. So you actually add a 50 ohm resistor.
It assigns port 50 ohms, yes. Like when you choose the port, it asks you to what impedance you assign, and by default it is assigning 50 ohms.
Okay, right.
Yeah.
So this is the difference. Yes. Thank you.
Mm-hmm.
So my name is Jaime Molins. I'm a PhD student from the Politècnica University of Valencia. And my presentation is entitled Design Procedure for 5G IoT Multiple Port Cavity Box Antenna. First of all, I would like to thank my advisor, Eva Antonino, Marta Cabeda, and Miguel Ferrando for their support in my thesis. So here we have the outline of my presentation. First of all, I will do a brief introduction about the global 5G spectrum, the indoor base station, and the premium design and the motivation of this presentation. Then I will switch to the design procedure, which will include a characteristic mode analysis and also a full wave analysis. So in the end of the presentation, I will propose a final design and we'll talk about the conclusions. Okay, so here we have the global 5G spectrum. Here we have, like, as you know, 5G will have bands from 600 megahertz up to 71 gigahertz or even higher. So for the early deployment of the 5G, the bands which are going to be used are the sub-6 gigahertz bands. So they will range from 600 megahertz up to 6 gigs or so. The reason behind that is that there are already a lot of applications working on that bands. So also from the 2G, 3G or 4G communication systems, there's already a deployed infrastructure. So it will be easier for the 5G to be deployed on that frequency and not in the millimeter waves that are still under research. So there's a growing demand on the indoor base station antenna. The reason is that the high standards of the 5G in terms of data rate, number of connection, and so on. And this kind of antenna will provide connection to indoor scenarios with poor signal level. So the requirements for this antenna are they have to be a wideband or multiple band solution. They have to have multiple independent ports with high isolation for MIMO compatibility. Also low envelope coefficient correlation for MIMO compatibility and high efficiency. And if it's possible, they have to be easy manufacturing and low cost. So here you have four recent design from 4 recent articles. For example, this one is a dual port broadband antenna. Here you have an annular ring with 4 ports with wideband behavior. And And this one is a triple port wideband antenna. And here we have a dual polarization antenna done with 2 cross dipoles. So the motivation of this presentation is we have been previously working with 4-port cavity box antenna. Like this one, for example, here we have a cavity. It is fed with 4 T-shaped monopoles, and this one is fed with 4 L-shaped monopoles. The problem of this design is that the resonances, they are a combination of the cavity and the feeding. And then when you do the analysis, it's difficult to identify the nature of each resonance. So we would like to simplify this design process, and we would like to do the characteristic mode analysis. Okay, so about the pros and cons of the characteristic mode analysis. About the pros, it calculates modes with the absence of feeding, and then this information you gather, it is good for getting information about the natural resonance of the structure. So then with that information, you can properly design the kind of feed. So about the cons is that you lack the feeding impedance references, so you cannot get proper matching and isolation between feed information. So generally, the characteristic mode analysis is performed in 2D and EC and canonic structures. So in this case, we are going to perform it in 3D structures, so it's going to be quite challenging. So the strategy we are going to follow is, first of all, we will do the characteristic mode analysis of the backing. In this case is the cavity. And then with this information, we will design the feeding, and we will do a full wave analysis in order to get the feeding information. So the goal in this case is not to present a really optimized and a really optimized design. And it is more about presenting a simple procedure for understanding and designing a complex cavity back design. Okay, so let's move to the design procedure. As I said, we have 2 steps for designing. So the first step will be focused on the characteristic mode analysis about the backing of the structure. And what we're going to do is to do a parametric study with B. We're going to check how the modes change when B is decreased or increased, in this case, from 0 to 25. And when the characteristic mode is done, then we will place the 2 feedings, and we will do the full wave analysis. Okay, talking about the first step, as I said, we will do the characteristic mode analysis of this cavity, and we will going to settle A, which is this distance, this U distance, to 100 millimeters for this analysis. And then what we're going to do is to shift B from 0 up to 25. It is really important to notice that when B is equal to 0, you can check that this cavity becomes a square ground plane. Why is this so important? So it is important, but because people who is familiar to modes, the square plane, ground plane, the modes are well known and well studied. So it will be a perfect initial point in order to check how the modes of this ground plane change when B is step by step increased. So we will check how will the modes change. So then, talking about the second step, we will complete the information we gather in the characteristic mode analysis with the feeding information. So we will choose with the information of the previous step, we will choose the optimum feeding, and then we will repeat the analysis for finding the optimum B in terms of isolation between ports and optimum of the input impedance. So finally, when we gather and we get together the information done with step 1 and step 2, we will propose an optimum design. Okay, let's move to the characteristic mode analysis. Before we continue, I would like to just briefly introduce the theory of characteristic mode. So it provides a set of currents on an arbitrary structure, and it gives a physical interpretation of the radiation mechanisms of the structure. So it will help to determine which kind of feeding it is optimum in your configuration. So characteristic modes are obtained solving this eigenvalue problem. So we use the generalized impedance matrix. Here we have the imaginary part and the real part. And it is calculated using the method of moments. So with that, we can calculate the eigenvectors and eigenvalues. So the eigenvalues gives really useful information about the resonance of the associated modes. So When the eigenvalue is equal to 0, the mode is at resonance. When the eigenvalue is lower than 0, the mode stores electric energy. And when the eigenvalue is higher than 0, the mode stores magnetic energy. So the attribute we are going to use in this presentation is the characteristic angles. And what we need to know is that at resonance, when the eigenvalue is 0, the characteristic angle is 180. So here it is our initial point. So we are going to analyze the 6 first resonant modes of the ground plane. Remember that the ground plane it is detailed when B is equal to 0, when the cavity becomes the square plane. So here we have the vertical mode. It has minimum here and the top and bottom. Here we have the horizontal one. It has minimum on the left and the right. Here we have mode 3, which it has minimum on the 4 corners and maximum in the middle of each side. Mode 4, it has the minimums on the center of each side and maximum on the corners. Mode 5, it has a minimum in the center of these 2 sides and maximum on the center of these 2 sides, and also minimum on the corners. And lastly, on mode 6, it has a minimum in the center of corner. So what we are going to do now with this cavity is to capacitively feed this cavity. So for capacitively feed an antenna or the cavity, we need a minimum of current. So which kind of modes are going to be excited? So we check the minimum of current. So mode 1, 4, 5, and 6 will be excited with a capacitive feeding because they have a minimum here where we are going to place our monopole. So mode 2 and mode 3, they will not be excited. So now what we're going to do is mode by mode, we're going to analyze how the mode change when we increase B from 0 to 25, from the ground plane until a high cavity. So for the first resonant mode, mode 1, it resonates at 1.6. So if we check when B it is increased, the resonance frequency it is increasing. So you have to be careful if you want to keep a minimum resonance. If you increase too much B, you will shift the minimum frequency of your design to higher frequency. So in this case, we do not recommend to have values higher of 17.5. Then if we switch to mode 4, this mode, you can check that when it is 0 or 6.25, it is not, it doesn't resonate, but it is really close to the resonance. But step by step, if you increase it, for example, to 12.5 or 17.5, it begins to resonate. So, but you have to be careful because if you continue increasing B, you will shift to higher frequency and also the slope is beginning to increase. So it is important to have a quite flat slope. Otherwise, you will get a narrow band behavior. So sorry. So we need to have values for mode 4 in between B of 12.5 and 17.5 millimeters. Then for mode 5, it is quite simple to identify. I mean, when you increase B, you are shifting the frequency to higher frequencies. So we do not recommend to have values higher than 20 millimeters. Otherwise, it goes to really high frequency. Also, the last mode, this mode is mode 6. It resonates at 3.25, and as before, when it is increased, it is shifted to higher frequency. But in this case, it is really noticeable that for values of 20, 25 or so, the slope is getting higher, and then you can get a narrower bandwidth. So we do not recommend to have values higher of 17.5. Okay, so let's switch to the full wave analysis. So here we have our final design. So we are going to complete with the feeding information with a 50 ohms impedance reference. So we are going to place two circular monopoles here in the cavity using, we are going to capacitively feed the cavity with two circular monopoles. And as before, we are going to settle A, which is, I remember it was this distance, to 100 millimeters. And now we are going to try to find the optimum B in terms of input impedance and isolation between ports. So here we have the result of the input impedance analysis. So when B is quite low, we can check that the dynamic range is really high. So it will be really difficult, or in order to match this design, it will have a really narrow bandwidth. So we have to increase a bit in order to have a flatter response, or to have values closer to 50 ohms in real part, or to 0 ohms in imaginary part. So the best results are obtained when B is in between 17.5 and 20. The orange and the green curves, you can check that they are close to 50 ohms and close to 0 ohms in the imaginary part. And when it is increased, it goes back to have like a bigger dynamic range. So it is better to stay in terms of matching in between 17.5 and 20 millimeters. In terms of isolation, it is easy to identify that when B is increased, the distance between the monopoles is decreased. So the isolation will decrease also. So if we want to have a minimum value of isolation of 15 dBs, we can check that for B higher than 20, the isolation will be lower. So we have to respect that distance, that value of B of 20 millimeters, and should be lower than 20 millimeters if we have to have a minimum isolation of 15 dBs. Okay, so about the final design, this is the final design we propose, gathering all the information we did before. So we obtain quite a wideband behavior using this design, with a bandwidth in between 2.9 and 7 gigahertz, and an isolation always higher than 15 dBs. So this table summarizes all the analysis we did before. Here we have all the characteristic mode analysis and the full wave analysis about the isolation and the input impedances. We can easily check that for the modal analysis, when B is low, we get better results, and when B is quite high, we get not that good results. Also about the isolation, it is better to have low values of B. Then the limitation comes about the matching. So matching, we get the proper results in between 12.5 and 20. So if we gather all the information together, we can check that the best result will come for B equal to 17.5. Even in between these two values will be the best results we gather with both simulation with characteristic mode analysis and full wave analysis. So B in between 12.5 and 20. And in terms of A, will be in between A divided by 8 and A divided by 5. About the conclusion, we can conclude that a wideband two-port antenna has been obtained using the proposed methodology, and the characteristic mode analysis of a complex 3D structure has been performed using as a references a 2D structure, which is the square ground plane. So the characteristic mode analysis gives really useful information regarding the minimum frequency and the bandwidth we can achieve, and the best result we have obtained are for B, for values of B lower than 20 millimeters, in order not to compromise the bandwidth and the minimum frequency. So A will be equal to the wavelength at the minimum frequency. Also, about the full wave analysis, it is required for the 15 impedance reference, and in terms of matching, the best results has been obtained for B in between 17.5 and 20 millimeters. And isolation should be lower than for values lower than 17.5 millimeters in order to have good results. So summarizing here, if we want to have a design with a minimum frequency of 2.9 gigahertz, we need an A of 100 millimeters, which will be the wavelength, and B should be in between 12.5 and 20 millimeters, which is in terms of A divided by A and A divided by 5. So here it finishes my presentation, so feel free to do any question you like. Thank you.
Okay, thank you, Jaime. So yes, we think we have 10 minutes for questions. So raise your hand if you're interested in asking something to Jaime.
I have a question. So I saw that you did with the cavity, like the modal analysis. Now, but have you done, so do you know what effect the cavity is making on the antenna, or the antenna is actually the part of the cavity here? Yeah. No, did you do the modal analysis of just that, like the circle?
We did the modal analysis just of the cavity, and we were.
Oh, okay. Not with the antenna.
Yes, just checking the potential of the cavity in order to be fed, not all together. Maybe this could be continuing in further studies, but just the cavity in order to check when B is changed to see the potential bandwidth we could achieve, but not as a whole yet.
Okay.
Okay, thank you.
I might have a question, Jaime.
Yeah.
How does it compare to cavity modes, like if you close the cavity? I mean, did you have an analysis about this? Can you tell us a little bit?
It's something we didn't do, but could be interesting to do just the correlation in between the model, the characteristic modes and the cavity modes. But it's something I cannot give you more information with because we didn't do it. We should be like analyzing, just replacing the same cavity, like placing two cavities together and do the analysis. But we didn't do it yet. So I will take it into account for a future simulation in order to see the correlation, but I don't know yet.
Thank you. Indeed, it would be interesting because in the cavity we have 3D fields. You know, we don't only have like the current mode. So that's like 3D fields
that's true.
That can probably help you. So you have another degree of freedom actually. So you can place it kind of everywhere.
Yeah, I agree. Yeah, that could be really interesting. It is true.
Thank you. Are there any more questions in the?
Hassanin is asking.
Yes, Hassanin, please.
Yes. Thank you for the nice presentation. Well, I can understand this is a raw study, initial study to check the cavity potential, which is very interesting. But at the end of the day, your introduction was about antenna elements, base station antennas, right?
Yeah.
And also, I'm not sure if you have shared any radiation performance of the monopoles in the cavity or not. I might.
No.
I was on another call at the same time, so I'm not sure if you have shared this or not.
No, I didn't share anything. It was just like an initial analysis about. I mean, we have been working in some other design. But in this case, it was just checking the potential and the comparison in between just a square ground plane and then checking how the modes change when you like become this, or you shift this from this square ground plane to a square cavity, and step by step check how the potential of the characteristic modes are shift in order to check a wideband performance. But we didn't do in that detail about the radiation, about the radiation behavior.
Fair enough. One comment just about this, because if you are meant to use this as in base station where there is multiple ports used concurrently.
Mm-hmm.
I think one of the interesting stuff is to monitor the phase offset between the two, across the modes between the two ports, and use that phase offset to use them as an phased array.
Okay, but you're thinking about feeding at the same time the monopoles or independently?
Well, yes, feeding
Okay.
the phase time and monitoring the phase distribution across the cavity to see at each, you can have multiple modes, multiple beams at the same time from the same port, basically.
Okay. So I will take it into account for the next time. Thank you.
Yeah, nice work. Thank you.
Thank you.